My name is Seihuan, and I'm a graduate student in the Biomimetic Robotics Lab at MIT. For ICRA 2022, I'm presenting my work titled Online Optimal Landing Control of the MIT Mini Cheetah. We motivate this work by considering the open problem of safe recovery for quadrupedal robots. While many quadrupedal robots have demonstrated impressive acrobatic capabilities, there has been relatively little focus on the motions needed to recover from high velocities. Due to the complexities involved with reasoning about contact and the nonlinear dynamics, prior work on quadrupedal landing has often been handled with simple fixed impedances at relatively low velocities. To that end, we present a predictive optimal controller that safely lands the Mini Cheetah quadruped from roughly 6 times its body height in both simulation and in hardware. As is common in locomotion controllers, we use a hierarchical control architecture consisting of a high-level model predictive controller and a low-level tracking controller. The contribution of this work is in the online computation of the landing MPC. Given some sensed falling state, a neural network generates a sketch of the landing trajectory. This is used as an initial guess to the nonlinear trajectory optimization formulated for landing and solved online on the robot. While contact is not detected, the robot holds some optimized touchdown pose with joint PD control, then tracks the solved trajectory after making contact with whole body control. The formulation of the landing trajectory optimization is as follows. The dynamics of the quadruped are approximated as a single rigid body model with kinematic constraints. The optimization finds single rigid body model state trajectories, foot locations, ground reaction forces, and joint angles through the predicted horizon. We choose to minimize the terminal cost that consists of the deviation from some reference final state, typically a stationary state. The main difficulty with this optimization is in its nonlinear and brittle constraints, the Jacobian relationship between forces and torques, contact complementarity, and the kinematics make this optimization challenging to solve online. Furthermore, the optimizer is prone to finding local minima and is highly sensitive to the initial guess provided. In the bottom right is a visualization of an optimal landing trajectory with this formulation. However, offline, we can explore these solutions and discover trajectories that are both kinematically and dynamically feasible over a wide range of falling conditions. Despite the approximations to the model, the generated trajectories appear visually similar to landings demonstrated by quadrupedal animals. We generate a labeled data set of these trajectories with their respective falling conditions and train a neural network to approximate these trajectories in the data set, as has been done in other work. The output of the network can be considered to be a rough trajectory sketch that is close to the optimal solution, but not exactly the same. By starting the optimization with a guess close to what the solution looks like, a local optimum is found orders of magnitude faster with a neural network warm start than from starting the optimization with no guess or with a relaxed single rigid body warm start. These videos showcase the Mini Cheetah landing in simulation and hardware from various initial conditions. The simulation environment fully accounts for rotor inertias and torque limits, and the Mini Cheetah is able to safely recover from significant velocities and orientations while falling. For practical reasons and limitations in state estimation, it was difficult to initialize the Mini Cheetah into a specific falling condition. On the right are videos shown at 0.5 speed. Instead, the platform was dropped from roughly 2 meters or 6 body heights above the ground to evaluate the controller. Future work will involve investigating how we can take advantage of actuated compliance to improve robustness, as well as estimate the body velocity while airborne. Recent work has also demonstrated impressive results from directly using the outputs of function approximators, which is being explored as well. Finally, it is possible that alternative solvers and control schemes may be more suitable for the optimization task at hand and need to be benchmarked against the current work. Thank you for watching, and please feel free to reach out with any comments or